Okay, everybody. So, I've already made a video about how to use the integral test, which is something that we can use to tell if certain kinds of series converge or diverge. Okay? But I want to talk about why it works. And in this video, this is not going to be a sophisticated mathematical proof, but I do think it will show you why the integral test works, why it gives you the result that it gives you. Okay, so quick example. So say we wanted to know if this series right here, a series from 1 to infinity, 1 over n, which is 1 plus a half plus a third plus a fourth, right? Keeps going. Say we want to know if that converges or diverges. We can use this integral, the integral from 1 to infinity, 1 over n dn, to tell if the series converges or not. The integral in this series will do the same thing. So this integral happens to diverge, all right? So that means that the series diverges. Okay, so that's like a very extremely brief overview of how to use the integral test. But here's what I really want to address now. What's the connection between the integral and the series? Why does it, if the integral diverges, why does that, show us that the series diverges? I mean, they look like two different things. But you might remember that an integral is based on a Riemann sum. So if you remember that from Calculus 1, already you might realize a little bit about the connection between the integral and the series. But nonetheless, I think the way to show you the connection between these and why the result of this one tells you something about this, I think it's best to show you some pictures, okay? So let's think about this integral. So this integral right here diverges, okay? Here's what that means. That if you take the curve y equals 1 over n, and let's say that the horizontal axis is n, from 1 to infinity, that this physical space, this area, is infinite in size, okay? That's what that means. When I say, or when I calculate that this integral diverges, that's one interpretation that can have, that this is infinite area right there, okay? So first we need to accept that. You might remember that, this is an improper integral, and, that is another topic, but, the way that we would do this is we would evaluate this integral from 1 to b, and then we would push the b to infinity, and whatever the result of that limit is the result of that integral. Well, that would be infinity in this case, all right? So that has infinite area. Now, so just sort of get that picture in your mind and think about it this way, okay? Here I have the same curve, y is equal to 1 over n, from 1 to infinity. Okay, it has a horizontal asymptote, but I put these rectangles on there. Okay, so same curve, right? Same curve is up there, same space, but now the rectangles. And I make this claim to you that the rectangles represent the series from 1 to infinity, 1 over n. Do you see why? Do you see why those rectangles could represent the series? Well, how big is this first rectangle as I've imposed it on this curve? Okay, how big is it? What's its area? Well, it's 1 space wide, and if I put 1 for n, then y will be 1. Okay, so it's 1, all right? And then what about this one? How big is this rectangle as I've imposed it on the curve? Well, its width is 1, and if I put 2 to find that point right there, and here that's going to be a half, okay? So it's 1 by a half. Okay, so its physical area is a half, okay? And then what about this one? Okay, so that's 3. I put it in the curve. Its width is 1, and its height is a third. All right, So here's what you get: 1, a half, a third, a fourth. If I kept going, a fifth, a sixth, and so on. Okay? So now that's as I've imposed those rectangles on the curve. Now, imagine if you added them all together, right? That would be the series. If I said, okay, 1 plus a half plus a third plus a fourth, that would be what this series is. And as far as my picture goes, that's the area of this rectangle plus this rectangle plus this rectangle plus this one, and so on. Now, as I've drawn it, isn't it true that the rectangles, like their total area, is more than this? Like, if you added up the total area of every rectangle, which does in fact represent that series, wouldn't that be bigger than the area under that curve from 1 to infinity? Well, you look at the picture. The rectangles are taller than the curve. So yeah, it's going to be more. So that's where the integral test works for us. Okay? The area of those rectangles is more than the area under that curve. But we found the area under the curve was infinity, right? You know, this integral from 1 to infinity, 1 over n dn was infinity. It had infinite area to it. So, all right, what does that mean? It means that the total cumulative area of the rectangle was more than infinity. Well, that's a problem. You can't be more than infinity. You know, it's like saying, remember those rectangles, remember what they represent? It's like saying this series, 1 plus a half plus a third plus a fourth, etc., is more than infinity. Okay, well, that would just mean it diverged. If all of this has to be more than infinity, then it can't converge, right? I can't say, well, this series converges to, I don't know, 5, for example. Well, 5 is not more than infinity. Could this series converge to 10,000? Well, no, I mean, 10,000's not, nothing's more than infinity. So the series has to diverge, okay? So it's really all just because the integral represents the area under the curve. That's infinity. And I can make the series be these rectangles that are a little bit bigger than that. So that's why if the integral diverges, the series diverges. Now you can make a similar argument for the convergent case of the integral test. Remember, in the integral test, the other side of the coin was that if the integral converged, the series converged. You can make a similar argument as I've done here for that. It's just you would impose the rectangles to be a little bit less than the area under the curve. You'd represent the series that way, okay? But the argument is similar. Anyway, so I think I'll let you explore the flip side of the coin on that. But as it is, I just wanted to show you a way to understand why the integral test works.